Thank you very much for the kind introduction and for having me today. So I wasn't quite sure what the mandate was for a talk. I thought that I would sort of tell you about the awesome time we're having at Inflammatix, and then a little bit about sort of the path that I took to get there, and sort of how an idea starts and the different path we take from grad school and beyond. So some disclosures then. This is all, of course, in hindsight, and so it looks great in 2020. Who knows? If I had to repeat it again, I'd probably be much less successful. A lot of the successes I'll tell you about were totally based on luck and timing, as I'll go through. And I will try not to pitch you on why Inflammatix is great, but I personally think it's awesome, and that bias is going to come through. So just a little bit about what we are doing now. Inflammatix is a 2-year-old startup, venture-backed. So raised our first round of funding from DARPA and then from Coastal Ventures last year. Spun out of research that we did at Stanford over the last 5 years or so, and I'll sort of tell you some of that story. Local company, about 13 people now, and probably about 2 years away or so from having a product on the market. So this is the problem that we started trying to solve, which is that when you go to a physician wondering whether or not you need antibiotics, that physician is guessing when they make a prescription decision. And this is something that I used to live out all the time as a surgeon. So when folks come in for major surgery, you have about a 5% chance of a post-op infection. But almost everybody that's in the hospital has symptoms of an acute infection. You get fever, you get a high heart rate, you get a high white blood cell count. And so it's really, really difficult to know which of those patients need antibiotics. And if we treated everybody, then we'd be treating 95% of people sort of inappropriately. And so I started the research looking for a new way to diagnose post-op infections, but what we found was sort of much broader. It was a way to diagnose really any kind of acute infection. And when we looked into, especially the sort of the traditional sort of primary care where everyone has been, right? Everyone here has had a cold or flu-like illness, and you go to the physician and you want to know one thing, which is, do I need antibiotics or not, right? You have viral infection, there's sort of nothing to do other than rest and fluids, unless it's influenza. But if you have a bacterial infection, of course, you need antibiotics to help you get better. And it turns out that the guidelines don't support any kind of microbiological testing in an outpatient setting because there are no tests that are really any good. There are sort of antigen-based tests. Maybe some of you have gotten a strep throat swab in the past, but they're really inaccurate. There are newer syndromic-based panels that can do a PCR for actual bacteria, but they're really expensive. And they're also sort of one-off. If you don't have strep, it doesn't mean that you don't have a bacterial infection. It just means that you don't have strep. And then, of course, we can actually culture bugs, but it takes a long time, and given the timing, most people just end up leaving with an antibiotic prescription anyway. So as a result, every major society, the American Academy of Pediatrics, the American Academy of Family Physicians, the Infectious Disease Society of America, recommend that when you go to your doctor's office to see whether or not you need antibiotics, the doctor just makes a guess. And when we look at the statistics, they're wrong about 30 to 50% of the time. So very, very frequently, you end up with antibiotics that you don't need. And of course, sometimes, although it's less frequent, you miss giving antibiotics to patients that do need them, and that can have really, really devastating consequences, even including death, especially in children. And so what we wanted was a product that could say, look, let's tell a physician right at the time you come into a clinic or the emergency room whether or not the patient has a bacterial or viral infection, so we can make a fast decision about who needs antibiotics. And so that's what we set out to do. Now the issue is that lots and lots and lots of companies, both big and small, lots of startups too, focus on, well, let's try to diagnose bacterial infections by looking in the bloodstream to see if bacteria are floating around, right? So there's sort of a newer onslaught of molecular diagnostic devices that can really, really quickly sort through the blood and see, are there bacteria present? Perfectly reasonable way to look. The problem is that for most infections, there aren't bacteria in the bloodstream. So if you have a skin and soft tissue infection or pneumonia or a UTI, the body's very good at keeping those bacteria locally walled off and not present in the bloodstream. And so you can go looking as much as you want for bacteria in the bloodstream, but if it's negative, it doesn't necessarily mean the patient doesn't have a bacterial infection. It just means they don't have a bloodstream infection. And so if you actually look at the numbers here on the graph, in patients with frank sepsis, right, an overwhelming, devastating infection, the numbers are like something like half of patients have a bloodstream infection. If you just look at a much less severe, sort of everybody showing up to an emergency department with a potential infection, it's closer to 10%. And in fact, if you looked at an outpatient setting of patients who are diagnosed with a pneumonia, it's 2% of patients have a bloodstream infection. So the vast majority of patients, there's really no way to establish whether or not they have an infection. And so what we'd like to say is that standard diagnostic technique of looking for bacteria in the bloodstream, it's not just like looking for a needle in a haystack, it's like looking in haystacks that frequently have no needles in them for a needle. So we wanted to do something different. And so this is the sort of traditional, how are we different from what else is out there? Lots and lots of companies have these bug-focused diagnostics. They're frequently looking for infections that aren't present in the bloodstream, so they're missing a lot of bacterial infections. They can frequently amplify things that aren't necessarily infectious, right? So you can get either commensal bacteria or just contaminants from the skin showing up in the PCR, and they're really slow. So what we do at Inflammatix is we measure the immune system. So the immune system has evolved over millions and millions of years to be very sensitive to know whether it should be reacting to a bacterial or viral infection. And some of my early PhD work, but frankly mostly work by other people, has shown that there are a lot of pattern recognition receptors that the immune system uses to very quickly distinguish, is this a bacterial or viral signal, and then it changes how the immune system reacts. So at Inflammatix, what we do is we read those signals. We look at gene expression patterns in the white blood cells, and that tells us is the immune system reacting to a bacterial infection or a viral infection or sometimes non-infectious inflammation entirely. So we can detect the presence of really any infection as long as the patient's having symptoms. We can be diagnostic and prognostic, so we can also tell sort of how overwhelming the immune response is. And we can be really, really fast, because this material is very abundant, right? There's lots and lots of RNA, and so we can amplify it very quickly. So, just to sort of motivate for you a little bit about how well this actually works, this is all validation data for a set of just 7 genes, 7 host immune genes, that we can use to determine whether an acute infection is bacterial or viral. So the numbers at the top there, what you're looking at is 24 pooled cohorts from all around the world. So this is kids and adults, inpatients and outpatients from every populated continent. And the width of the colored bar at the top indicates the size of the cohort that we're testing in. And the blue violins indicate patients with bacterial infections. The red violins are patients with viral infections. The y-axis is the score that we use. And you can see overall the numbers are at the very top of the screen. There's 1,000 patients. We had an area under the curve, which is a measure for measuring diagnostic tests, of 0.93, which is excellent. In particular, at a single cutoff that you see here in the dotted line, we had a sensitivity of 95% with a specificity of around 70%, meaning you could both rule in and rule out bacterial infections in patients of interest. This was all independent but retrospective data, and so in prospective study, we've looked in single cohort at Stanford, which is an AUC of 0.88 for distinguishing bacteria from viral infections in a really sick population, and then in sort of a more bread and butter population, a multi-center trial in Australia, where we showed an AUC of 0.91 across inpatients, outpatients, and the ICU, but in particular, if we look just at the less sick patients, those that were not hospitalized, we were nearly perfect, an AUC of 0.98, so 98% accurate in separating bacterial from viral infections in that outpatient setting. So this is now being commercialized with the help of some partners, and we'll get into that in a little bit. I thought that it would be helpful to understand what it is that we fundamentally do, why we see ourselves as really a data science company and not necessarily just a diagnostics company. In general, lots of people have looked for these kinds of immune signatures in the past. We're not the first to come up with the idea. If you go back to sort of the advent of the DNA microarray around 15 or 20 years ago, this was one of the first use cases, actually. Someone thought, hey, we can look and see if we can find a signal for the presence of an infection. And so over the years, more than 100 studies have now been published in looking at the immune response in patients with acute infections. The issue is that when you look at just one cohort, if you're going to look for a bacterial and viral signature, typically you look in a very homogeneous cohort to drive up the statistical power to detect differences, right? So you wanted to look for a signature for bacterial from viral infections, and you look in just kids at just one hospital with, only in the ED within 2 days of symptoms. And that's fine. Maybe you find a signal for separating bacterial and viral infections there. The problem is that when you move to adults in a different country in an outpatient setting, the immune response looks very different, right? So our insight was to try to leverage all of this really vast clinical heterogeneity, different geographies, different infection severities, different clinical settings, different kinds of infections, et cetera, and look across the public domain and say, can we find enough data sets that really cover all of the kinds of settings in which patients have acute infections, and put all of those data sets together, and then see if we can find a single fingerprint for the presence of infections across all of those settings at once. And so that's what we did, and that's why we've sort of been able to find these very reproducible fingerprints. And so what we have now is essentially a machine learning pipeline that's generally applicable, right? So we can sort of start with lots of data sets, the heat maps on the right, start with lots of data sets, feed it into the beginning of the pipeline, and sort of what comes out the other side is relatively robust, generalizable gene signatures for the diagnostic in question. And so Inflammatix now has, so far, well, not just Inflammatix, but also our lab at Stanford with Professor Patry, who's the PI. We've now validated over 8 areas of application. Sepsis and acute fevers are sort of the first that were commercialized with Inflammatix, but in general, we've also done a lot of global health type tests like tuberculosis, dengue fever, malaria. We've done other outpatient tests like influenza versus other respiratory viruses and autoimmunity. And we've done other inpatient tests like organ transplant rejection and drug responsiveness, always prospectively validated, and the results continue to be very successful. But what it means for the business is that instead of trying to build a specific device for sepsis and another device for outpatient clinics that would work for the fever test, and yet a third device that would work under a tree and sort of severely resource-limited settings for ultra low cost, there's no way we can engineer separate cases with ideal product market fit for each one of these tests. So we have essentially a software business model wherein we work with diagnostic instrument manufacturers to put our content into those existing channels and get them to market that way. And hopefully we'll have some announcements over the next couple of months, and we'll love to discuss more if you have specific questions there. But I thought for this talk it might be interesting to spend some time sort of going over how did we arrive here? Were we having an awesome time doing it the whole way? And are there any sort of lessons that can be gleaned? And I think the 3 things that I thought about looking back about, if we've had any success, what does it do to? It's really it's timing, it's luck, and it's hearing no a lot, but keeping going anyway. Timing's a funny one. I don't think we necessarily realized it was a good time. It just was, and we happened to be lucky about that. The pipeline that we put together really was only possible because we happened to sit at the confluence of a number of events that had nothing to do with us. Like I briefly mentioned, microarrays have been around for 15 or 20 years. And early on, it was very clear that there was sort of a reproducibility crisis with signatures being found in microarrays. And so the NIH decreed that there should be public data sharing of microarray experiments and established the Gene Expression Omnibus along with a few other national societies around the globe for microarray data sharing. And that was done about 15 years ago. And since then, microarrays have been accumulating. In fact, right now, if you go to the GEO website, there's 2.4 million publicly available microarrays for reanalysis and reuse. If any of you think this is a great idea, you can go home and download the data yourself and start competing. At the same time, around 10 years went by and people began to think, geez, instead of sort of just reanalyzing somebody else's data, maybe we should begin to put these things together. And so a lot of statistics and math were done into finding ways to cross-normalize, co-normalize data set from different kinds of microarray platforms so that we could begin to pool these data. And some of that early work, certainly not all of it, some of the work was done in a tool use lab while he was still at Stanford, where my PI and now co-founder, Pravesh Kantri, was a postdoc. And so they had, sort of happened to be at the right place at the right time to begin to understand how to knit these data sets together. And by the time I came along and said, geez, you've built all these statistical tools, maybe we should try to refine them into actual diagnostic tools, and I particularly want to look at sepsis, it happened to be that over 100 data sets had now accumulated in the public domain, so we really had enough to go back and begin to sort through and say, maybe there's signal here for the condition of interest. But even that only got us to our first Science Translational Medicine paper in 2015, which is where we showed that a reproducible gene signature for the presence of infections could be found. We were among the first to show that there was a reproducible signature that could be found, but that's so far from translation, right? Our signature at that time happened to have 11 genes in it. Well, that's great, but one of the pushbacks we got was, so what? Nobody at the current time has a device on the market that can measure 11 genes in under an hour, which is what you need for clinical application. We said, sure, but it's just proof of concept for now, so trust us, we'll keep working. It happened to be that right around that time, there was an advent in highly multiplex molecular platforms, most notably the BioFire platform, but others as well. And certainly what we've seen is sort of a groundswell over the last couple of years of instrument manufacturers building devices that can measure highly multiplex targets at once. So maybe 15, 30, 50 genes all at once in under an hour. Again, nothing to do with us, but we couldn't deliver this in a clinically reasonable time frame if it hadn't been for those other technologies coming to market. Yet another one is that we needed money to do this. There had been a lot of diagnostic failures. Of course, most notably, you all know the Theranos story, but even before that, and much less publicly, a lot of VCs had lost hundreds of millions of dollars and other diagnostics companies that had just been commercial flops. And so there's sort of, if we had done this maybe 2 years prior, we wouldn't have been able to get any funding. But it happened to be that the advent of things like Braille and sort of the traditional cancer-focused precision medicine had gotten a lot of the community excited to get back into this precision medicine diagnostics field. And then the last is that even when we had the money, the instrument, and the gene set, if it didn't have an economics case, it wouldn't have mattered. But it turned out that the National Institutes of Health, along with the CDC and other national bodies, had decided that sepsis was completely out of control as a hospital measure for quality, and so implemented a bundle that included rapid diagnostics for sepsis, and that in particular would reduce hospitals' capitated payments if they weren't treating patients appropriately. So basically, millions of people around the world working on totally disparate things happen to sort of converge on, geez, now appears to look like the right time to build a product that can use a gene set, that can be delivered rapidly, that someone will actually pay for, and that there's enough development dollars up front. So I'll say we were very lucky in timing. There's sort of a personal story of serendipity, and I'll just mention that every time looking back in my life, I thought I was going to be doing something. I was always wrong. So you sort of start off when I was in high school, and I knew which college I wanted to go to, and I didn't get in. So I found myself at the wrong college, knowing that I was going to go in and get a PhD in neuroscience. And along the way, someone said, maybe you should do an MD, PhD, and you'll be able to, quote, ask better questions. Fine. So applied MD, PhD, and only got into one med school. And thought that I would go and do neurosurgery. It sounded really cool. Thank God I happened to get to Duke. At Duke, it's a very unique program. They have really only one. It's unique in the sense that they have clinical training before you do your PhD. So I actually spent a couple of weeks doing neurosurgery, realized I hated it, found that I liked taking care of patients with sepsis instead, and ended up doing this sepsis and trauma training that led to what I was going to do. And I thought I was going to be general surgeon, switched into anesthesia, thought I was going to be anesthesia, switched back into general surgery. Found myself in general surgery at Stanford, ended up dropping out to pursue bioinformatics. And then once I dropped out of general surgery to pursue bioinformatics, thought that I would do academics, and ended up founding Inflammatix. Let me just say, whatever the next 5 years will be, I'm sure it's nothing that I think now. Embrace serendipity, go where the interesting work takes you. It's worked out for me so far. All of those choices were incredibly tough, and I think that you're here, right? You're at Berkeley. You're doing well, but you're going to face tough choices. And one thing that I constantly forgot and had to remind myself was, you know, if you have choices, you're doing pretty well. The choices can be really tough. Switching careers and sort of trying to decide what's best next. The Yogi Berra quote came up, when you come to a fork in the road, take it. I think that each time I've made a change, just for what it's worth, I've found that the things that seem to matter under the old regime fall away incredibly quickly. And suddenly you're on a new path, and those are the choices that matter to you now. And typically you don't end up with regret about the path not traveled, because you're off doing something new. Living with no, we've been rejected constantly. Personally, my academic career has been pretty good looking backwards, but actually it's been mostly rejection. In particular, the funniest one was the firm rejection from the bioinformatics postdoc at Stanford. They said that physicians would never be successful in bioinformatics. So I had to reapply. Our first SDN paper had a formal rejection, and we simply said, no, this needs to go in, so we reject your rejection, and ultimately we're successful in that. Certainly we've had a ton of early grants rejected. In particular, one of them really spurred me, ended up to found Inflammatix. We got the most annoying reviewer feedback that you can get, which is, if this were a good idea, someone else would have done it already. Fine. I've talked to dozens of investors, probably close to 100 investors who said no. It's okay, you just need one to say yes. And then of course, still as we go out now, right, we think the data's great, but some partners just say, no, it's not for us right now. So how do you get to yes? That's how we have an awesome time. You just have to be persistent, honest to God. It's sticking with something that you know to be right. You have to be politely persistent, that always helps. I say paperwork, everyone will have something, well, you know, yeah, but just fill out the thing, whatever it is. Don't fight about filling out the thing. Drown people in paperwork, do whatever they want so that they don't have excuses to say yes. Be persistent, be positive in yourself, know that what you're doing is worthwhile, and continue to be persistent. Summarize a pitch. If you can't sell what you want to do to somebody else, maybe they don't understand why it's important. Say yes to other people when you're hearing no a lot yourself. You'll be surprised where those avenues take you, even if they seem maybe like they wouldn't yield you anything up front. Just say yes, especially if you're hearing no, and be persistent. We say that sort of, if we say an idea enough, it'll become true, and that is potentially both bad and good. Bad, of course, is remember that there is confirmation bias. So just convincing yourself that the pathway links the two molecules together or whatever. You can make up a lab experiment to disprove or to prove something that is not true, almost certainly. But in the good case, really, the more you say something, the more a small idea gets heard by more and more people. They begin to believe it's true, and then they believe that you're a good person to do it. And then remember, of course, that not everything's in your control. Just remember that ideas take time to grow. A couple of asides I'll just mention. Build in time off, especially now in the age of iPhones. It's so easy to sit on Twitter, or Facebook, or whatever. I do this all the time. But I remember very clearly that at least one or two of the sort of eureka moments in how to move forward were just time in the car with radio off, where nothing else was going on, time in the shower, that kind of thing. And then the last thing I'll talk about career-wise is that I've trained in bench techniques, I've trained in medicine, I've trained in surgery, I've trained in anesthesia. Now I'm in business. Every single one of those things yields something that I use today, right? Whether it's sort of understanding just enough about PCR to understand what the lab folks we've hired are doing in the lab, understanding enough about clinical medicine to be applicable in something else. Whatever you're learning, learn it deeply. It will come back, it will be of use. Techniques cross-pollinate, etc. Just a little bit, so this little guy came into our life about a year ago. So life's going to happen, make sure you make time for it. It's really important. And then of course it's a team effort, so my greatest thanks for all of this goes to the people that have been with us along the way, from Claude, my PhD mentor, through to the Stanford trauma team that told me to take time off in bioinformatics, to Pravesh Kantri, who worked with me on the early research, to Jonathan, my co-founder, who's now sort of back running Inflammatix, and of course, my family with whom I couldn't do it. So I'll take any questions. And just so you know, I won't be around at the end of the lunch period, so feel free to reach out if you want to follow up on any of this. Thanks very much.